Alright, so this is Wiley 6C. And it's a McLafferty rearrangement, so... okay, so 6C... McLafferty rearrangement of 4-methyl 2-octanone. It's a ketone. And again, they put this 2 pathways. I don't know what they mean by this. Secret to me. If somebody knows, you can let me know. Alright, so here let's draw out the molecule of 4-methyl 2-octanone. The ketone is on the 2nd carbon and the methyl is on the 4 carbon. So I had to do some background information to be able to do this problem. I got it from page 435 from Solomons and Friel, 10th edition. Okay, so then when they give an explanation of McLafferty or rearrangements, which is, okay, so carbonyl compounds, which is like this ketone, carbonyl compounds with a hydrogen on their gamma carbon undergo fragmentation called the McLafferty, sorry, I'm getting a little tired, rearrangement. Okay, before I do the McLafferty rearrangement, the mechanism, okay, there was a little bit more background information. I went and looked up, I didn't know what a gamma carbon was, and it's kind of important. So, gamma, symbolized by that Y, carbon. Okay, so it says the first carbon atom after the carbon that attaches to the functional group, which in this case is the carbonyl ketone, is called the alpha carbon. The second beta carbon and the third the gamma carbon. I got this from Wikipedia. Just go to the functional group page. And then when you're in there, search for the word gamma. Alright, so now let's do the mechanism. So here we have, they gave us, it's a carbonyl group attached to, okay, so let's just draw it out. Alright, so this y here, y is just, it says y can equal r, it can equal h, it can equal o, r, oh, and I guess etc., right? And so on. Alright, so what happens is, in a McLafferty rearrangement, the double bond of the carbonyl group gives both of its electrons to the gamma. So okay, this is right here, this is the alpha, right? Because it's one carbon away from the carbon that's attached to the functional group. So this is the alpha, this is the beta, this is the gamma. So it gives its, this double bond gives both of its electrons to the hydrogen attached to the gamma carbon. And so it takes it for itself, and then these two electrons come between the bond of the gamma and the beta carbon, okay, both of them, both those electrons, and then the bond between the beta and the alpha carbon breaks because it gives both of its bonds to the bond between the alpha carbon and the carbon directly attached, I'm sorry if my hand was blocking, directly attached to the carbon that has the functional group. I hope my hand wasn't in the way, but, and then what you get alright, just in case my hand was in the way, I'm just gonna go over it one more time. So the double bond between the double bond here gives both of its electrons to the hydrogen attached to the gamma carbon, and then both of the electrons from that bond go between the gamma carbon and the beta carbon. The bond between the beta carbon and the alpha carbon splits because it gives both of its electrons to the bond between the alpha carbon and the carbon attached to the functional group. And then, so, right, it splits right here, and then this H comes over to the oxygen, which we see right here, and so we get the H from the gamma carbon attaches to the oxygen. This becomes a single bond, and this becomes a double bond, but was over here, becomes a double bond right here, plus right, this becomes a double bond. This R is this R, and when this bond gave both of its electrons, this became a double bond, and we can see the double bond here, and this bond had been broken. Sorry if I over-explained that. So now to actually get on to the problem itself. So the problem was 4-methyl 2-octanol. Octanone, it's a ketone. The two pathways things, I don't know what they mean by this. Two pathways. Alright, it's a McLafferty rearrangement. McLafferty. So let's rewrite this one more time. And this time I'm going to label, this is the gamma carbon, the beta carbon, the alpha carbon, and then I'm just going to put this H here because remember it's the H that's on the gamma carbon that interacts. So what happens is the double bond from that's attached, that's on the carbonyl ketone group here, gives both of its electrons to this hydrogen. Then, so it plucks it off. This gives both of its bonds to this, to the bond between the gamma and the beta carbon, forming a double bond. And then the bond between the beta and the alpha carbon breaks, giving both of its electrons to the bond between the alpha carbon and the carbon directly attached to the functional group, making this double bond. So, right, this is the M plus, this is pre-fragmentation. It fragments and we get positive charge stays on the oxygen plus the ion. Do they show where the ion goes? I guess the radical? I don't see any radical here. I don't see any radical. I don't know. I'm not going to think too hard about it. So there's the right, so here's the double bond that was created right between the gamma and the beta. Here's the double bond that was created between the alpha and the carbon attached to the oxygen. So Wiley asks the charge of the molecule, of course, or not of course, it's +1. They ask for the mass divided by the charge. This one, out of all the hydrogens, the oxygens, the carbons, and it equals 58. Now, just for people who are going to be writing this in Wiley, Wiley was annoying about it. So just pretend that Wiley gives you these brackets. Remember, when you have these brackets, you don't have to like specify where the charge is. And just write the molecule like this without adding any charges or anything like that. Just put that in there and Wiley should give you the credit. Okay. Thanks. Bye.